Hello everyone and welcome to MacTech 40, and today we will going to solve a fantastic question of refrigeration air conditioning that has been asked in Indian Forest Service 2021, and this is of 20 marks. I am writing given data over here. A single cylinder single acting compressor having bore and stroke, bore diameter that is D 16 centimeter, that is 0.16 meter, and stroke length. So stroke length is given 24 centimeter and it is 0.24 meter, running at the 120 rpm. So this is n is given, and the indicated mean effective pressure, so p indicated PIM, I'm denoting with PIM. Indicated mean effective pressure is 2.2 bar, and pressure limit of the refrigeration system operating on ammonia, that is 9.74 bar and 2.47 bar. That means condenser pressure is 9.74 bar and evaporator pressure, that is 2.47 bar. The temperatures of the refrigerant at the entry and the exit of the condenser. So from the entry it is 40 degree and exit 17 degree Celsius. But corresponding to evaporator condenser pressure, that is 9.74 bar, the saturation temperature is 24 degree. That means it indicates that this is the case of superheating as well as subcooling also. Now this is, and the condenser is water cooled. So in cooling water across the condenser is 15.45 kg per minute. So mass flow rate of the water, that is 15.45 kg per minute. Now the inlet and outlet temperature of cooling water, that means TW1, that is 16 degrees Celsius, and TW2, that is 24 degrees Celsius. Now the mass of ice produced, and in evaporator this is from condenser side. The condenser is water cooled and we are producing ice. So mass of ice Mi, that is 56 kg per hour. The mass of ice produced is 56 kg per hour at water at 20 degrees Celsius. That means water initially, that means Ti1, water is entering at 20 degrees Celsius and converting into Ti1, Ti2, and converting into 0 degree Celsius and making ice, and latent heat associated with it, that is 335 kilojoule per kg. Now what we have to find: compressor power, mass flow rate of the ammonia, coefficient of performance, and dryness fraction of ammonia entering the compressor. That means this is the entry of the compressor is wet, and here property table of the ammonia is given, and we have to also draw TS and PH diagram for this. So we will first draw TS and PH diagram and then we will proceed for the next. Okay, so here superheating as well as subcooling also there, and this is throttling process. I am denoting with 1 as a compressor entry, 2 as a condenser entry, 3 as a condenser exit, and 4 as a evaporator entry, and this is the process. Similarly, pH diagram for this will be like this: 1, 2, 3, and 4. This is the cycle. Now this is the diagram. Now what we have to find: compressor power in kilowatt. So compressor power, first thing that we can find out, like so whenever compressor is a power consuming device, so compressor power P, that you can find out by indicated mean effective pressure multiplied by L E into N divided by 60. Here only single cylinder, single acting, so this equation is not only, we did not have to multiply by number of cylinders. So indicated mean effective pressure, that is 2.2 bar, that means 2.2 into 10 to the power 2, stroke length 0.24 meter, that is area pi by 4, that is cross section area of the bore diameter 0.16 meter square, into n. RPM is 120 RPM divided by 60. So when you simplify this, you will get 2.12 kilowatt. 2.12 kilowatt, that is the power required. This is the answer of first question. Second thing that we have to find is mass flow rate of the ammonia. I am denoting with MA. What is the mass flow rate of the ammonia? So now we can find out this. Some maybe say that in the generally we are finding out in the evaporator section, that is what is the refrigeration effect multiply with H1 minus H4. But how to find H1, because it is a in wet region, so how to find dryness fraction? If we have entropy data, then we can compare S1 is equal to S2, but here no entropy data is given in table. So what to do? We know that condenser is water cooled condenser, so whatever the heat gained by the water, that is water is 15.45 kg per minute, water is changing the temperature from 16 to 24. So whatever the amount of heat is that is gained by this water, that has to be rejected from the condenser. And mass flow rate of the refrigeration and this whole system, if we consider this whole system as a control volume, then it will become closed system. So whatever the mass flow is entering from evaporator, condenser, compressor, that will remain same. So for this we have to apply heat balance. So heat gain by water, heat gain by water is equal to heat rejected by ammonia in condenser. So what, how much heat is gained by the water? That is m dot water, Cp of water into Tw2, or you can say that what is the notation we have used? Tw2. Okay, so that is Tw2 minus Tw1 is equal to heat rejected by ammonia. So ammonia, how much ammonia heat is rejected? Ma into H2 minus H3. So say it as a equation number 1. Now we don't have value of H2 and H3, and here mass flow rate of the ammonia that they have asked in the per minute, and the water flow rate data is also given as per minute, so that is very good. So now how to find H2 and H3? So look at the TS diagram. 2 is in the superheated region at the 9.74 bar, and 3 is the subcooled region. So enthalpy at point 2, that is given by H2 is equal to Hg plus Cp T2 minus T2 dash. Here T2 dash is what? 2 dash is this point. 2 dash and 3 dash. 2 dash, 3 dash. So what is the enthalpy of? And this is at 9.74 bar. So what is the Hg value? That is 1482.53 plus 2.87 into 40 degree, that is the exit inlet of the condenser. And what is the saturation? That is 24 degrees Celsius, that is saturation temperature. So when you solve this, you will get as a 1528.45 1.45 kilojoule per kg. Now H3 similarly, here it is subcooling there. H3 is equal to HF minus Cp T3 minus T3 dash. T3 dash and T2 dash will remain same. HF will be from the property table, that is 312.87 minus 4.61 into 24. That is a sorry, here I have made one mistake. That is T3 dash minus 30, that is 24, that is saturation, and subcooled temperature is 17 degrees Celsius. So now if you solve this, you will get 280.6 kilojoule per kg, and the exit of the condenser and inlet of the evaporator, that they both have the same enthalpy because expansion is isenthalpic. So H3 is equal to H4. So we have both have H2 and H3 value. Put it in equation number 1. So equation number 1, mass flow rate of the water that is 15.45 kg per minute. Cp of water, in the question it is given that 4.1868 4.1868 multiplied by temperature rise of water, that is 24 minus 16, and mass flow rate of the ammonia that we have to find, and the difference is 15, enthalpy difference 1528.45 minus 280.6. So when you solve this, so what is the mass flow rate of the ammonia? You will get 0.414 kg per minute. 0.414 kg per minute. This is the answer of our second question. Now the third thing that they have asked is coefficient of performance. Coefficient of performance, that is how much COP. Now for the COP, we know the formula of COP, that is refrigeration effect upon power produced. So how can we find refrigeration effect? Refrigeration effect, we know that the amount of heat that has been taken in the evaporator, and how much amount of heat is taken, the amount of heat rejected by water to become ice. So Mi and specific heat of water, and it is at initially 20 degree and it is becoming at 0 degree, and latent heat associated with this ice Mi into LH. So what is the 56 kg per hour is water is converted into ice. So 56 divided by 3600. Why? Because uh, we want our answer in kg per second to make our refrigeration effect in kilowatt. Cp of water is 4.1868 into 20 plus 56 divided by 3600 into latent heat is 335. So when you simplify this, you will get as a 6.514 kilowatt. This much amount of refrigeration effect, and substitute this value. Refrigeration effect is 6.514 divided by power is 2.12. So what will be the COP? You will get as COP 3.07. 3.07, that is the COP, and this is the answer of our third portion, that is in how to find COP. Now the fourth portion is dryness fraction of the ammonia entering the compressor. So how to find dryness fraction of the ammonia? That is X. So we know that what is the refrigeration effect we are getting from the amount of heat rejected by water to become ice. So that has been taken by the refrigerant ammonia, mass of the ammonia, into H1 minus H4. From TS diagram you can say that H1 minus H4, that has been in evaporator section, this much. So refrigeration effect is 6.514. Ammonia mass flow rate is 0.414 kg per minute. So we have to divide by 60 to convert kg per second. And H1 we have to find out. We don't have H1, and H4 we have, because here we have found H3 is equal to H4, 280.6 kilojoule per kg. 280.6. So when you simplify, you will get H1 enthalpy at 0.1, and that is equal to 1224.65 kilojoule per kg. Now look at the, and H1, that is enthalpy at evaporator section, evaporator exit. So at evaporator side, that means at 2.47 bar, the enthalpy of vapor is 1445.2, and here we are getting enthalpy 122.4, which is less than the Hg at evaporator pressure. So that means it is in wet region. So how to find dryness fraction? H1 is equal to HF plus X times HFG, that means enthalpy of evaporation. But here HFG data is not given, but we know that Hg minus HF is known as HFG. So H1 is 1224.65 is equal to HF. HF at the, this is 135.82 at evaporator pressure, that is here I have to write at evaporator pressure, that is HF is equal to 135.82 plus dryness fraction X, and Hg 1445.2 minus 135.82. So when you solve this, you will get X is equal to 0.83. So this is the dryness fraction at the exit of the at the inlet of the compressor, or you can say that exit of the evaporator. So this is the answer, all the four answers that we have to find. If the entropy data is given, then the calculation will be quite shorter. Okay, so yes, and here one more thing, the one thing that I forgot to mention, that here H2 Hg plus Cp, and here Cp of vapor and here Cp of liquid of the refrigerant you have to take, because H2 is in the vapor region and 3 in the liquid region. So as Cp of vapor and Cp of liquid, here it is given 2.87 and 4.61. The value that I have taken 2.87 and 4.61. Okay, this thing you should keep in the mind while solving the problem. But at the last in the question, what there is one other thing also they have to ask. They have asked, if the state of ammonia at the entry of the compressor is either dry saturated or superheated, then comment what will happen to COP and why. So here what happened, okay, so this is the our given data, and here 0.85, 0.83 dryness fraction. If you shift this line from dry saturated state, okay, so the refrigeration effect will be going to increase. This is 1 point shifted to here, so refrigeration effect will increase, and the compressor work, there is change is very less. The increase in compressor work is very less due to changing in from wet to dry saturated. So in this case COP will increase. But if you further superheat over here, let me denote with some other pen. If you further superheat, so the compressor work will going to increase rapidly. So in that case, the relative increase in the refrigeration effect and compressor work will decide whether the COP will increase or not, because here 1 point will shift from here, so 1 to 4 the amount of refrigeration effect is going very high, but simultaneously the compressor work is also increasing with considerable amount, this much amount, delta P times. So in superheated case, in most of the cases COP is increased, but you have to write that uh, the COP increase or decrease, the final decision will be upon the relative values, the relative increase or decrease in the value of refrigeration effect and power consumption. So this is the answer, and this is the way you have to solve this in the exam also. So I hope you like this video and like this solution. Tomorrow we will see some new questions, and thank you for watching this video, and like this video, subscribe this channel, and share with your friends also. Thank you.